So the question is, in photoelectric effect, the work function of a metal is 3.5 electron volt. The emitted electrons can be stopped by applying a potential of minus 1.2 volt. So the options are A. The energy of the incident photon is 4.2 electron volt. B. The energy of the incident photon is 2.3 electron volt. Option C. If higher photon frequency be used, the photoelectric current will rise. And option D. When the energy of photon is 3.5 electron volt, the photoelectric current will be maximum. So before we solve this problem, let us go into the basics of photoelectric current. So we have a metallic surface or any surface that has free electrons. So these surfaces or these conductors will have free electrons on its surface as well. When electromagnetic radiation of energy E, which is equal to h mu, where mu is the frequency of incident radiation, is used, electrons will absorb the energy from this incident radiation and will be emitted from this electron surface. By electron surface, I mean any surface which has free electrons. So this emission of electrons due to incident radiation of suitable energy is called photoelectric emission. So mathematically we can put this as h mu, which is the energy of the incident photon, that is equal to phi plus kinetic energy. So the emission of electrons occurs in two steps. First, part of the energy will be used to liberate the electron from the surface. That energy is called work function and is denoted by this symbol phi. Work function. And the next, the remaining part of the energy which is absorbed by the electron will be used up to supply some kinetic energy to the electron, to the liberated electron. So all the energy bearing the work function which is used up already will be used up to supply some voltage, I mean some velocity to the electrons, because we obviously know that kinetic energy is of mv square. So depending upon the energy left, the electron will acquire some velocity. So there is a special case where we can actually consider the electron will have no kinetic energy at all. That is, the velocity of the electron will be zero in some cases when the energy of the incident radiation is sufficiently small. So for such radiation, let us define a new frequency called mu naught. So the energy of such incident radiation will be equal to work function. Because the velocity is zero, there won't be any kinetic energy. The supplied energy will be entirely used up for work function, that is to liberate the electrons from the surface. So this frequency, we define it as threshold frequency. So threshold frequency means the minimum amount of frequency or the minimum frequency of the incident radiation required to liberate an electron from the electron surface. So this doesn't give any definitions from what is the possible kinetic energy. So if the frequency of incident radiation is threshold frequency, the kinetic energy of the electrons liberated will be zero, and the entirety of the energy supplied will be used up as work function. So let us substitute this value into this equation. H mu equal to h mu naught plus kinetic energy. So kinetic energy will be equal to h mu minus h mu naught. So this is the first equation. So as per photoelectric effect, electrons are emitted. So what if we introduce an opposite pole electrode so that we can conduct an external circuit to produce some electricity? So this will serve up as cathode because this has excess of electrons, or electrons are being emitted. And this will be the anode. So this will be the cathode from where electrons are emitted, a photoelectric surface, and this will be the anode. And there will be an external circuit, some external load. Alright. So electrons, after being emitted through incident radiation on this surface, will be liberated, and depending upon their kinetic energy will reach this surface, which is the anode, and it will pass through the entire external circuit to come back to the cathode. So we have an electricity flow. But when we supply the anode with an equivalent negative energy, an equivalent negative potential, so as to repel the electrons away from the anode, like for instance, instead of the positive charge, we are giving it an negative electric potential, some V volts. The electrons, despite their kinetic energy and their emission from the surface, will be repelled by this anode due to the presence of negative potential. So at one point, there will be a minimum potential at which even the fastest electron, which is liberated from the surface, will be left out and won't enter the anode. So at such a point, the potential through this entire circuit, and coincidentally the photoelectric current through this entire circuit, will be zero. So such a minimum potential is called stopping potential, and we define it as Vs. Alright. So when we give an energy Vs, the total energy for E electrons with E electron charge will be kinetic energy equal to E into Vs, because the maximum kinetic energy of the electron is being repelled by this stopping potential. So this kinetic energy will always be equal to the energy supplied through this stopping potential. So Ke, which is kinetic energy, equal to Vs. That will be equal to H of mu minus mu naught from this equation. So we have to use this equation and this equation for further calculation. So we shall put the equations on one side of the board for further reference. So the incident energy equal to work function plus kinetic energy, which is equal to phi plus E into Vs. So this is the first formula. Second formula, E into Vs equal to H of mu minus mu naught, and H mu naught equal to phi. So let's go on into the laws of photoelectric emission. So for the photoelectric current to be high, like for instance we have initially a photoelectric current of 1 ampere, we have to increase this photoelectric current to 2 amperes. We have to increase the number of charges, because current is the rate of flow of charge. So if we are to be able to increase the number of charges flowing through the unit area of the conductor, we will be able to get a photoelectric current which is higher in value. So if for 1 ampere of photoelectric current we have 20 electrons, from 20 into 20 power 4 electrons. For this we have to obtain 2 into 20 power 4 electrons. So technically an increase in photoelectric current is due to an increase in the number of electrons emitted. So to have a larger number of electrons emitted through the surface, we need to have a larger amount of photons hitting on the surface. So if we have larger amount of photons, it would mean that the intensity of the incident light is very high. So it means that photoelectric current is directly proportional to the intensity of the current or the intensity of incident radiation. So h mu, which is the energy of the incident photon, is being used for a single electron interaction. No matter how much high frequency we have or how much high energy we have, it will be used up only to increase the kinetic energy of that particular electron. It won't be used to increase the number of electrons emitted. So photocurrent is independent of frequency. It is independent of frequency. So the next case is that stopping potential is dependent on the kinetic energy. We have proved to this point. So let's come back into the problem. The work function is given as 3.5 volt, electron volt, and the potential that is supplied, stopping potential that is supplied, is minus 1.2 volt. So in terms of electron volt, we can put this as E into V is equal to minus 1.2 electron volt. So what is the total energy? Energy equals 3.5 minus of 1.2 electron volt. So why we are using this minus symbol is the kinetic energy and the supplied stopping potential energy are exactly at opposite directions to each other, because they repel, and the kinetic energy of the electrons is being prevented by the stopping potential to prevent the electrons to reach the other surface. So whatever the energy the stopping potential has, kinetic energy will have the same equal potential but with an opposite magnitude. So 3.5 minus of minus 1.2 electron volt, because we are not using the kinetic energy term here, we are using stopping potential energy term. So 3.5 plus 1.2, that is equal to 4.7 electron volt. So as per option A, the energy of the incident photon is 4.7 electron volt. So option A is true. And option B, which says that energy of the incident photon is 2.3 electron volt, is false. And option C, if higher frequency photon be used, photoelectric current will rise. So we have already established that photoelectric current is independent of frequency. So no matter how much high the frequency of the incident radiation is, the photoelectric current will remain the same. It is dependent only on intensity. So option C is also false. And option D, when the energy of photon is 3.5 electron volt, the photoelectric current will be maximum. So for photoelectric current, I already established that the electron emitted should reach the anode at any point. So when the electron energy of the photon is 3.5 electron volt, when the energy of the photon is 3.5 electron volt, we can see from the equation that the kinetic energy will be 0. So when the kinetic energy is 0, there won't be any energy left for the electron to absorb and get accelerated at some velocity and reach the anode. So there won't be any transmission of electrons, so there won't be any photoelectric current. So technically, when the energy of incident radiation is 3.5 electron volt, which happens to be the same energy required as the work function of the metal, the kinetic energy will be zero. So photoelectric current will actually be minimum, that is equal to zero. Photocurrent will be minimum. So this option D is also false. So the correct option is energy of the incident photon is 4.7 electron volt. Hope you understood the solution. Thank you. The stopping potential versus frequency plot of a substance is shown in figure. So I will just draw the figure for your reference. So this is the given graph. So we have to determine the threshold wavelength from this equation. So to find the threshold wavelength, we need to know what is the threshold frequency, which is the minimum frequency required to emit an electron from the metallic surface as per photoelectric current. So we know that work function is equal to h mu naught, where mu naught is the threshold frequency of the metal. So in that case, we find that the kinetic energy of the system or the electron which is emitted through this process will be zero, because the entire energy which is supplied at the threshold frequency is being used only for the work function, and no energy is utilized for kinetic energy. So kinetic energy will be zero. So incidentally, stopping potential means in a sense negative potential applied to prevent any electron at the maximum kinetic energy from reaching the opposite anode in a photoelectric conductive system. So in that case, kinetic energy is zero, which means that electron energy supplied through the stopping potential will also be zero, which means stopping potential itself will be zero. So at the threshold frequency, stopping potential is zero. So from this graph, we can find that at the stopping potential 0 point, the threshold frequency, is 5 into 10 power 14 hertz. So threshold frequency is 5 into 10 power 14 hertz. So we have found the threshold frequency now. From this we have to find the threshold wavelength. So by the properties of wave mechanics, we already know that speed of the wave is equal to frequency into wavelength. Alright. So from this, we already know what is wavelength. We already know what is the frequency of the material or the frequency of the incident radiation. So we can replace this term. So wavelength will be equal to C by mu naught. That is equal to 3 into 10 power 8 meter per second. which is the speed of light or speed of any electromagnetic radiation, by the threshold frequency 5 into 10 power 14. So let's divide this. We will obtain 0.6, 3 by 5 is 0.6 into 10 power 8 minus 14, that is equal to 0.6 into 10 to the power minus 6. So to convert this into Armstrongs, I am multiplying and dividing by 10 power minus 10 into 10 power minus 10 by 10 power minus 10. So I am evaluating this further. So 0.6 into 10 power minus 6 plus 10 into 10 power minus 10, that will be equal to 0.6 into 10 power 4 into 10 power minus 10, that is equal to 6000 into 10 power minus 10 meters, that is equal to 6000 Armstrong. So the options that were given were 5 into 10 power 14 meter, 6000 angstrom, 5000 angstrom, and cannot be estimated from the given data. But we have already estimated that the threshold wavelength will be 6000 Armstrong. So the option A, 5 into 10 power 14 into meter, is wrong. Option B, 6000 angstrom, is the true option. So the final solution is 6000 angstrom. So we have determined what is the final threshold wavelength for the required solution. Hope you have understood it. Thank you. The variation of maximum kinetic energy of emitted electrons with frequency mu in photoelectric effect currently. So the options given are So these are the given options. So we have to find the correct graph that identifies the relationship between kinetic energy and frequency of incident radiation in photoelectric effect. So we already know that the equation relating kinetic energy and the frequency of incident radiation is h mu equal to h mu naught plus kinetic energy. So I am going to put a table over here. So kinetic energy is Ek, and mu. So when Ek is 0, when this term is taken away, and h mu equal to h mu naught, this means that the frequency will be mu naught at Ek equal to 0. And we can easily identify that at other points of kinetic energy, this represents a linear equation in the form y equal to mx plus b. So we had to identify a graph where at y-axis, or the kinetic energy is 0, the value of frequency turns out to be mu naught. And from that point, a linear straight line must be evolving. So in this equation A, we find that at Ek equal to 0, the value of frequency is also 0. But we know that at Ek equal to 0, the value of frequency is mu naught. So this option is wrong. And at option B, we find that at Ek equal to 0, frequency has some particular value which is not identified, and as you can see here, this is a linearly increasing equation. So the slope of this equation is also positive. But this equation has a negative slope, because with increase in the value of x, we actually find that the value of frequency is going down. And at the same time, at Ek equal to 0, although we find that the frequency is mu, which is some particular value other than 0, the value of frequency should not be high at Ek equal to 0. But at the same time, at mu equal to 0, we find that Ek has some particular value which entirely goes against this rule. So option B is also wrong. And let's come to option C. At Ek equal to 0, we find that frequency has no value. So this option is also wrong. At option D, at Ek equal to 0, we find that the frequency is equal to mu naught as per our predictions using this equation. And it is a linearly increasing equation from